Basically, over the next more or less hour, I'm going to try give some partial insights into this question. Okay, so here it says for machine learning, and of course we know machine learning consists of many different types of problems. And the first question I'm going to ask is, should we use parameterized quantum circuits for learning probability distributions? Okay, so the first thing that you have to understand is, what even is distribution learning? When I say distribution learning, what do I mean? So I guess the setup is probably familiar to most people. You have some unknown probability distribution that you would like to know. Perhaps it's the distribution over price, different prices for the stock market the next day. And you get samples from this distribution, and you feed this into some learning algorithm. And the goal of the learning algorithm is to output some hypothesis distribution Q. And I should say, like, how to output a distribution is not such a simple thing. It's a little bit subtle. And what I mean here, like, by outputting a distribution is that you output an algorithm to either sample from the distribution or evaluate the probabilities of the distribution. But there's a subtlety hiding in here. OK, and now the point is that we want to explore the power of quantum learning algorithms for this problem, and in particular, parameterized quantum circuits. That's what this whole talk is about. And so how do you do this with parameterized quantum circuits? Well, you take a circuit, you parameterize it, you put some thetas in the gates, and then you measure the circuit, and you sample from a distribution, which is this Born distribution. And of course, this is a parameterized distribution now, because all the gates are parameterized. And I guess everybody here knows that then the idea is that you feed the samples from this distribution into some classical computer, which calculates a loss function and tells you how you should update the parameters of your model. So this here is called a Born machine. And it's not the only approach to doing distribution learning with parameterized quantum circuits, but it's one of them, and it's the one that I'm going to make statements about. But I think the ideas, the techniques, the methods can be applied to the other proposals that people have made.
Can I ask a very fundamental, naive question?
Yeah.
Why do you hope this is even better than trying empirical method for anything?
What do you mean by empirical methods?
You just look at samples and then build some, averages over those.
I mean, so you've described a very simple classical learning algorithm,
yeah.
and you could try it, and you could.
Why do you hope this one is better?
I mean, I'm going to prove that it's not. Like. Yeah. Okay. Okay. So thanks for the ad. Okay, but we want to prove something, so we have to work within a formal framework. And a lot of people have already mentioned the PAC framework, and this is the one that we're going to take, which is a natural choice. And so the first thing that we need to do is we need to assume a concept class. So this is the set of all distributions, which we know is hopeless to learn. There's no structure in the set of all distributions, nothing to hold on to. So we assume a concept class, which is a subset of all the distributions which share a common structure, and we're going to try design our learning algorithms to exploit that structure. The point is the structure is essential for learning. OK, now what we want is that for every element of the concept class, if we feed samples from that element into a learning algorithm, then what the learning algorithm should do is with high probability, it should output some distribution within some small epsilon ball around the distribution you would be given samples from. So it's called probably approximately correct learning, because what you want is that for all the concepts in the concept class, with high probability, your learning algorithm is approximately correct. Yep.
Do you really want proper pack here?
OK, here let's talk about proper pack to keep things simple. Of course, you can rephrase this in all the ways that you want. OK, so now in the ideal situation, the dream of every theoretical quantum machine learning practitioner is to find an example of a concept class which is quantum learnable, so learnable in the sense with quantum algorithms, and classically hard, and I should have here, and also practically relevant. We've already seen lots of examples where you can do things here that are practically irrelevant. So there's an omission here, but that's the ideal. And even more is we would like to show that we can realize that separation via a parameterized quantum circuit learning algorithm. So if I can find an example of a concept class that has a quantum classical separation that can be realized by Born machines, then you should really go invest in quantum computing companies, because we're showing that this is in business. OK, so now the question is, imagine I want to prove a separation between quantum and classical learning algorithms using quantum Born machines. The question is, what concept class should I pick? What class of problems, what class of distributions do I expect that I might be able to prove such an advantage for? Well, the answer is I should choose the output distributions of quantum circuits themselves. Why? On the first hand, we know something about these distributions, that they're hard to sample from classically, given a description of the classical circuit. And this kind of feels like a good starting point for a proof that they might be hard to learn classically. You have to do a proof, because like I said in answer to Maria earlier, the problem of learning to sample from the description of the circuit is different to the problem of learning to sample given access to samples. But anyway, you think that this might be hard to do using a classical computer. And at the same time, it seems plausible that maybe a Born machine can do it, because the Born machine has the exact right inductive bias, and all it needs to do is find the right parameters. So I would argue that if you're going to try prove something realistic for Born machines, this is the class of distributions you should consider. Yeah.
Can you give any intuition for how locality manifests itself in the proof? Like if you didn't have that constraint, what would be different about the output distribution?
Sure. So technically we're going to use properties of designs. So you put anything here that is a design and it's going to work. Yeah.
So I have to make a small remark.
Yeah.
If I'm not mistaken, for a proper pack, learning DNF is hard. But if I draw proper pack, then it's not. So I'm not sure that this is generic.
I'm going to get to reasons why I think this is weak, actually. I'm lying to you. There's something more you should want here, and it's going to come later in the talk.
Can I ask a question?
Yeah.
So are you going to be assuming convergence to something large hard? What happens if you have IQP type circuits where the algebra is super small?
It's all going to come. It's all going to come. Yeah. Okay. And so now, what we saw in Jens's talk is that these LQC distributions are indeed hard to learn quantumly. At log depth, there's this T-gate result that shows that they're not learnable. At polynomial depth, you can put PRFs in them. So we know that strictly in this PAC sense, there can be no separation between quantum and classical learning algorithms for the problem of learning these distributions. So again, this provides some evidence against using Born machines for distribution learning. But what about heuristics? Maria also mentioned this, and Rajan said it too. You can prove all sorts of worst-case hardness results. Learning neural networks, I forget who mentioned it in their talk, but learning neural networks is hard to do for neural networks in a worst-case sense, and yet they work extremely well. The point is, what we really want is heuristic algorithms. So what does this mean? Like I said, we have worst-case hardness results, which means that in the set of all LQC distributions, there's at least one distribution which is hard to learn. This is somehow like a cartoon where you can think about it. But maybe Born machines are still a good heuristic. And what this means is maybe they work on average. So maybe there's some sort of subset of these distributions such that for all of these distributions, it's easy. Okay, and also someone said earlier, you have to be careful about what on average means because it's with respect to a measure. But let's assume you can put a nice measure on here. And with respect to that measure, you want that a large fraction of these are easy. And this is not ruled out by the previous worst case hardness results. It could be that in the worst case, these things are hard to learn. But in practice, they all work. Jens always talks about NP easy problems. I mean, of course, we know that there are certain things are NP hard, like 3-SAT, but heuristics work really well for almost all instances. And maybe Born machines do it.
I'm citing industry people.
Yeah. But unfortunately, the answer is no. Born machines are not a good heuristic for these distributions, which I think provides even stronger evidence that these are a bad idea to do distribution learning with. Because, like I said, the output distributions of quantum circuits seem like the most obvious place to go try prove something. Okay. Earlier, Marco asked this question about, should we separate sort of Shor-based quantum machine learning from variational quantum machine learning? And so this is kind of a bonus slide where I give my answer to this question. And I try to provide a motivation for this kind of really formalized way of looking at learning. So imagine you want to try do something like I'm trying to do in this talk. Try give really good, rigorous evidence for or against using parameterized quantum circuits for a specific class of learning problems. I would argue that the first thing that you should do is you should study this problem with completely impractical distributions, like factoring. Because I think of this as some sort of necessary condition for quantum advantage. If I can't prove a quantum advantage in learning using something which is tailor-made for a quantum computer to get an advantage, why should I expect this to be the case in highly unstructured problems? So I view this as kind of a necessary condition and the first step on a longer road. But it's also definitely not sufficient. Of course, nobody is claiming that because there is a quantum learning algorithm that can run Shor's algorithm to learn some highly exotic distributions that encode factoring, that you should now go and try this to generate text. But something nice is that when you try to do this, you learn some learning theory along the way. And hopefully this is something that can help you later in your life. Okay, the crux is that this is not practically relevant. There's no doubt about it. So what would you do as step 2? Well, you do what I said in the beginning. You use everything you learned here, the setup, the tools, and you just replace the concept class with something which is more relevant, or from which you could try to draw some conclusions about parameterized quantum circuits. For instance, this is the one that you think they would be good at. And so try to prove something about that. OK, so here you've got the right inductive bias. You've introduced parameterized quantum circuits. You seem like you're on the right track. But it's worst case analysis. And we think that these things could be good heuristics. Like, we don't even want them. We don't expect or want them to be able to work on everything. So then you go to step 3. And you consider the same class with the right inductive bias. But you consider the average case. And now here you are like really making statements about the power of parameterized quantum circuit learning algorithms as heuristics. And so you've gone from not practically relevant to practically relevant. And I think this is the way that I see the answer to your question. OK, so let's carry on. So like I told you, yeah.
Sorry, why is it heuristic in the third thing? I don't get it. Like, why can't you analyze average case also in the rigorous setting?
Sorry, say that again?
Like, why call it why is the third one heuristic but not the second one heuristic?
I mean, so here I'm doing worst case analysis. Step 2 is worst case analysis. So if I prove worst case hardness of this, like there could still be good heuristics. But if I prove average case hardness, I'm also providing evidence against heuristics. Yeah.
Can you ask another naive question? Yeah. Do you have a list of distributions which you can learn well?
Sure, yeah. Like, take, for instance, product distributions, like over bit strings. Then it's like n coin flips. You learn the Bernoulli distribution on each coin. Gaussians, you can learn well from Hoofding. There's many distributions. There's many classes of structured distributions which are known to be learnable. Certain graphical models, we've heard in the last 2 days about like classes of graphical models that are learnable. Restricted Boltzmann machines with single hidden layers via alphatron. There's many that are known to be learnable. Yeah.
And just to exactly follow your thought, if you find that the average case does not work, this is a practically relevant result because it gives us a suspicion that it might not be working very well. But if you show that it works, we're still not there when we know something practically because that...
Exactly, like you said it perfectly. I would argue that if you prove that it's average case hard, you've provided pretty good evidence against using these in practice. If you proved it's average case easy, then there's still the chance that for like practically relevant distributions, it doesn't work. So you're right, but this is like the proof roadmap for someone who is skeptical, who wants to prove negative results, which has been me in the last few years. OK, so average case hardness, yeah.
If you prove that it's average case hardness, like maybe a skeptic could argue that the distribution that you chose is the wrong.
They could do that. They could do that. Like you have to have the core belief that this is like a reasonable thing to do to get evidence about the power of distribution learning. You're totally right. Yeah, I mean, but the problem is that, like, what would convince that skeptic? If I went and proved that quantum learning algorithms couldn't solve ImageNet well, but ImageNet has no structure for me to hold on. I feel like that's kind of, this is Maria's point, that there are definitely, like, the ultimate thing you care about is outside the realm of theory. And I would argue that this is kind of as far as you can go in like, TCS land. Yeah. OK, so now I promised you an average case hardness statement. So here's a theorem. That comes from this paper, which you can go look at on the archive. And remember, we care about like the fraction of the output distributions of local quantum circuits that are learnable. And so what we prove is that for any statistical query algorithm, so I have to tell you what a statistical query algorithm is, and I will do this later. But for now, just keep in mind like practically relevant. It turns out that almost all learning algorithms we know are SQ algorithms, including quantum-born machines. OK, I'll explain what it means in a second. And what we're interested in is, if I take a given depth of quantum circuit, and I insist that a certain fraction of those output distributions should be easy to learn, then how many queries do I need? Like, I want to put a lower bound on the queries. This is the way that we're thinking about it. And let's go through an example, and hopefully it becomes clear. So let me consider super logarithmic depth circuits. OK? And let me insist that 4/5 fraction of these distributions should be easy to learn. Then, in this case, we can prove that you need to have a super polynomial number of queries. So any learning algorithm that learns a 4/5 fraction of at least log depth circuits is using at least a super polynomial number of queries. This is a super polynomially average case hardness result for a constant fraction of distributions of log depth circuits. OK? But what we can also prove is that if your circuits are slightly deeper, OK, and of course, when you make the circuits deeper, you get more distributions. Then,
sorry, I think this is critical and I'm missing something. Yeah. What is the statement? That any learning algorithm which manages to get it right on 4/5 must have the super polynomial.
Precisely.
And this 450 is any of it.
Okay, there's a distribution. We put like a distribution on here.
And it's a worst case or any distribution?
No, like this is proven for a very specific distribution. We consider brickwork circuits, and we imagine the distribution where every 2 local gate is drawn from the Haar measure. So this is kind of like
So there might be another distribution which has 4/5, which doesn't.
I can't tell you any statement about any distribution. Like the average case is with respect to this typical random local circuit distribution that people think about. And this is a weakness, for sure. I'll be open about it. But it's the one for which you suddenly have designs and you can get moments, etc., etc., etc. Okay, and in this case, so now we had linear depth and we want to insist that our algorithm, I mean, this is a very, 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 very weak thing to insist. Well, all we want is that our algorithm succeeds on a fraction that is just bigger than some exponentially small fraction. So really, this is basically like saying, I want my learning algorithm to succeed like basically never.
Wait, is that omega or theta? Because omega can also mean 1, right? So
I mean, this thing is asymptotically greater than a decaying exponential. So in the, like
that also includes 1.
Yeah, okay, but like all of these are upper bounded by. So exactly, so let's think about. There's a good point. The easiest case, or the hardest case, is when beta is equal to 1, because then I'm insisting you should learn all the distributions. So the smaller beta gets, the easier the problem should get, because I'm insisting you learn less and less. And so now what I'm saying is, like, as you increase the circuit depth, you maintain hardness for successively smaller fractions.
Maybe for intuition, there could be only one circuit, and then you can learn it because you know it. It's only the one, right?
Sure.
So it cannot be smaller, this omega 2 to the n. It cannot be doubly exponentially small, because then it would fix a circuit and then.
I think about it differently. Like, I think this, like, thinking about successive beta is a good way to do about it. Like, if I tell you, please come up with an algorithm for me that should learn all distributions. This is going to be hard. Maybe this is what Vedran was saying, actually. But if I say to you, like, you only have to come up with a learning algorithm that learns one distribution, there's a trivial learning algorithm. You just hard-code it and you put it out. So we see that learning all of them is like the hard extreme. Learning just one of them is the very easy extreme. So we know that as you insist on being able to learn less and less distributions, the problem should get easier. Yeah.
I absolutely agree. That maybe my confusion is that because you have omega, all of those are included in this, right? It's not theta, so you're not asking it to just solve like an exponentially small region.
No, we're saying this should be for any beta like this. So like, that's it, exactly. For any beta that is larger than an inverse exponential. For any beta that's non-negligible in the crypto language. Okay, so we can show that for linear depth circuits, if I ask you to learn any fraction which is larger than an inverse exponential, then you're going to need an exponentially number of queries. And I'll advertise the talk from Wojtek and Louis, who actually, like, since we came up with this, have generalized this to not just any SQ algorithm, but any like algorithm that can make quantum statistical queries in different bases. They'll tell you what this means, but this is an ad for their talk, which generalizes, at least explicitly in their paper, this result here. And finally, there's somehow a silly one, which is maybe not worth talking about, but as the circuits go to infinite depth, then even if you want to learn a doubly exponentially small fraction of distributions, you're going to need a doubly exponentially large amount of time. I mean, not of time, of queries. That's important. So the point is that we have strong average case hardness. I think the most relevant line is to look at this one. And the point is that we really have strong average case hardness for learning the output distributions of local quantum circuits. And my claim is that this gives you some evidence that Born machines cannot be a good heuristic. Like you said, like, you have to believe my like reasoning to believe me. But I think it's reasonable. I think a reasonable person could agree with me. I think a reasonable person could also disagree with me. But like, this is my belief.
Sorry.
Yeah.
This is on the same theme. So is the conclusion the only thing I can do is to hunt for these few good examples and be happy with it? Because there I avoid your problem because I'm not in these kind of average cases.
I think the conclusion is that, I'll put it in a broader sense, that we know that all algorithms need to exploit some structure. And there has to be like an inductive bias that they can get hold of. And one would think that like the output distributions of quantum circuits would be like a good inductive bias. But this tells you like very concretely, and this like you can't disagree with me with, that like Born machines can't exploit the inductive bias of the output distributions of quantum circuits, so you have to look elsewhere. This is what I think the message from this is. Yeah.
I absolutely love this arguing. I think there's more of this type of thing where we not only explore, are there any problems that we can learn, but say like a bit more experimental, like we need problems that prove or give us an intuition for something, right? So I'm actually, yes, I don't really want to argue against it, but now with this inductive bias problem, if we think about, well, I'm just like trying to think now about neural networks, right?
Yeah.
They're super expressive, so could neural networks learn themselves?
Yeah, this is well studied. Yeah.
In some sense, I'm sure there's a lot of study about this. There's the teacher-student models of the statistical learning people, and but I'm wondering because neural networks plus stochastic gradient descent, obviously, as you very well know, have these properties that they just have a bias towards easier problems. So I wonder if the hypothesis is right that a model can learn a concept class easier that is generated by itself. Super interesting question, actually.
Yeah, and I mean, like, I have to be honest that, like, let me criticize this. And Vedran is the one who gave me this criticism a year ago or something. Like, you can ask, like, you could do the exact same thing for neural networks. Like, pick a class of neural networks, ask if they're learnable in the worst case. No, there exist hard instances. Ask if they're learnable in the average case. Also, no. But neural networks work extremely well. So there is, like, something here going on that we don't understand, but I think even classical people will say that.
Yeah. It's scaling. And these are asymptotic statements,
exactly,
right?
Exactly.
We don't scale.
Yeah. I mean, I don't know if you heard that, but Vedran said, like, it's true that these are, like, in asymptotic land, but anyway, yeah.
I missed that argument, but maybe you can repeat it. How would that look like for classical learner? We also know that in average case, classical machine learning is an average case hard.
Like, okay, there's a formal statement. Like, so here you would take, instead of the LQC distributions, you would take like the output distributions of like some depth 10 neural network with like some width. Like, I don't know what the actual statement is, but like there's some exact example that you can prove hardness, like average case hardness for. Yeah, I think it's like Clevans, these sorts of people that were mentioned, I think, in Patrick's talk. Yeah. Okay, so this was that, and I've shown you this theorem. And now I think I'm gonna skip the proof. And if there's time, we can come back to it in the end. Okay, so that was about should we use parameterized quantum circuits for distribution learning? And hopefully I convinced you that, like, at least for Born machines, my feeling is no. Okay, so now let's move on to supervised learning, regression. And we're going to take like a whole different approach here, but hopefully we'll be able to draw similar conclusions. Okay, so firstly, what is supervised regression? Well, in this case, you're given some data, which is tuples xi, yi, which are drawn from some distribution over some product set. Okay, so for us, x is always going to be some compact subset of Rd, and y is always going to be, you can just think of the interval 0, 1. And what you want is to learn a function from x to y, which minimizes the risk, which is defined as the expectation value of the difference between f of x squared and y squared when x and y are drawn from the distribution. So, like, I've set this up in a way that's possibly overcomplicated by considering a distribution here. But I could also just say, imagine like you're given samples xi and f of yi, and then you want to learn f. That's somehow like the simpler version of this.
Maybe parentheses around in the square of the difference?
Yeah.
That's the difference of the means or something.
Yeah, no, I saw this now. This is like the typical squared error. I wrote it wrong, I know this is too. Okay, so this is supervised regression. And now, like, I'm going to go through exactly what I did, like where we introduced Born machines to solve distribution learning. What do you do if you want to solve a supervised regression problem with a parameterized quantum circuit? Well, now what you do is you take a quantum circuit, and some of the gates you parameterize with theta, which are parameters that I'm going to update. And some of the gates you're going to parameterize by x, which is the data that's coming in. Because, I mean, you give me an x, it's a classical bit string. Like, I have to give that to my quantum computer in some way. And the way you do it here is by using that value of x to parameterize some of the gates that you do. Okay, when you do this, you get a unitary which depends both on x, the input to the function, and theta, some variational parameters. And then what you do is you can measure some observable, and you define the output of your function to be the expectation value of the state that you get after applying this parameterized unitary to the all zero state. So I think this is probably familiar to people who've worked with parameterized quantum circuits. I mean, I put here Z1, but put the observable of your choice. It works. Okay, and then again, you give this to a classical computer. It calculates the risk, which is basically the loss, and then it tells you how to update the parameters. So this is somehow like the thing that is extremely popular at the moment. I think this is a good model for it. This is like when Maria said, the first thing I think is I should try a variational quantum algorithm. This is what she's talking about as her kind of first intuitive idea of what to do. Okay, and now I'm going to change tacks. And instead of following the program that I sketched in the previous part of the talk, I'm going to follow a different program, that of dequantization. And so people have mentioned dequantization, and here I want to formalize it a little bit and tell you what that means if you haven't heard of it. So imagine that there's Alice. This is like a typical quantum computing story that has Alice and Bob. And Alice has a quantum computer. And Bob only has a classical computer. And now there's some data that defines a regression problem. And Alice can run a learning algorithm that involves a parameterized quantum circuit. She can do variational QML, basically. And what she gets out is some function which we're going to call FPQC. So it's the output of the parameterized quantum circuit that Alice trained in this typical way that you do in variational quantum machine learning. But now poor Bob, he only has a classical computer. And he also has access to the data. And basically, like what we would like is that Alice can do much better than Bob. So what we would like to prove in the dequantization, from a dequantization perspective, is that if Alice gives a classical description, imagine Alice gives a classical description of her circuit to Bob. So she can't do anything with it. She just has the classical description of it. And now imagine Bob has access to the data, and he knows what Alice is doing. Alice is very proud of her quantum computer. She doesn't think anyone can do as well as her, so she publishes the circuit that she's using. And now Bob has the data and a description of the circuit that Alice is using, and he's going to output some classical function. Yep.
When you say given the description, do you also mean given the parameters that you have to training?
No, I just mean the architecture. It's a good point. I mean like the graph that defines this. Yeah. And the generators, exactly.
Wouldn't the description of the circuit be like exponentially large if the circuit is too large? So we have to like have all the measures.
For sure, but I mean like you have similar problems like this in classical like complexity theory, in that like many functions, if you write out their truth table, it's exponentially large, but there can be a succinct description, like parities. You know that you should just take the inner products, for example. So there can be objects that, if naive descriptions, are exponentially long, but for instance, like brickwork circuits, they can be like arbitrarily deep, but I can give you a very like short classical description, which is just like the set of brickwork circuits up to like exponential depth, where every gate is the same, for example.
Okay, so yeah, so we're not assuming the whole like space of all circuits, because it might be
Exactly. Like we're assuming that Alice is working within the space of circuits that have efficient descriptions. But I think for any circuit anyone has ever tried, like there's an efficient description of this in the kind of existing literature. Okay, so now basically I think this models like the state of the world at the moment. There's companies that have, or like people that have quantum computers, and they're writing papers in which they say the architectures they're using. Like Maria compiled a fantastic list for us all to look at. And now classical people have access both to the same data and to the descriptions of the circuits that the parameterized quantum circuit people are doing, and they can also do learning. And basically we're going to say that this like variational QML setting can be dequantized if two things happen. If Bob can be efficient, if his learning algorithm can be efficient, and if what he outputs is basically as good as what Alice outputs. Okay, and now I accept, like we could argue about what efficient means. Like does efficient mean polynomial in the size of the problem, which is like RD, or does it mean like with at most a polynomial slowdown with respect to Alice? These are all variations of dequantization that you could ask about, and they're all fair, but yeah.
So in this definition of dequantization, it's not just about F, PQC, approximate FC, it's also about being able to train, to learn the problem.
I'm not sure what you mean by that. Can you say it again?
It's just because I usually think about dequantization just about being able to produce the output, but you also mentioned that Bob needs to be able to learn the problem.
No, like what I want is that, I mean, so when would this be like not a good idea? It would be if like Bob with this and this can produce this in what we consider a reasonable amount of time. Exactly. Like, I mean, I'm insisting that Bob should be a reasonable alternative to Alice. Yeah. Cool.
Question from Zoom?
Yeah, I have a question. Maybe for learning, there is involved computationally and statistically. So when you mention the hard, it could be the computational hard. It could be the statistically very hard to estimate. Like for example, in the statistical framework, any like learning method involve like the array loss function, how good you can learn, and also involve the class of distribution you wanted to learn in that part. Maybe when you talk about the hard, and it is really that how do you measure how like you're using the loss function you used, and what kind of class right now, like you mentioned the beta, and to produce like the good estimate.
Yeah. Okay. Like you're right. Like there's many variations that you can consider. Like the learning problem. Like the data can be like any concept class, any distribution over the concept class. There can be like any loss function here. Like I feel like this is a general definition that encompasses all those different scenarios. Like Alice and Bob are trying to solve the same problem. Alice can use the quantum computer. Bob only knows like what Alice plans to do. Okay. So now like. There was the question about which architectures we're going to consider. And my answer is that we're going to consider a class of architectures called re-uploading parameterized quantum circuit models. And these are like, I think, probably almost all the architectures people use that I'm aware of can be put into this framework. And basically, we consider big parameterized quantum circuits that consist of 3 types of gates. The first type of gate is a data encoding gate, a gate that depends on X, like the classical data you're given. The second type of gate is a trainable gate. And then there's W, which are fixed gates. So those are like C0 ladders or something like this. So we consider like the architectures we're going to try dequantize are these ones. And like if you take your favorite ansatz, it can probably be put into this form. Okay, and now you can measure any observable O, and this unitary depends on X and theta, and in the end you get this function in this way. Yeah.
Yeah, so here you assume the classical data is quite small set, is that right? Because it's not scalable. Right?
No, okay, so maybe this is an important thing to understand. So X here is like some single instance of the data set. It's not the entire data set. It's just like one data point. It's a vector in RD in the way that I set it up. So like, I mean, if D is exponentially big in terms of something you actually care about, then this will be hard. But like D normally sets the scale of the problem. So this is like efficient with respect to D. Okay, and now like I'm gonna add a restriction. That like now I confess that I'm like going into a smaller scale of models than all of them, and I'm going to restrict to a certain type of encoding gate. So I have the circuit. Some of the gates depend on X, and what I'm going to insist is that all these gates implement the time evolution of some Hamiltonian for time xj, where j is the jth component of the vector in Rd x. Okay, this is like both a restriction and something reasonable in the sense that a lot of models do use this. Okay, and now you're going to see that this Hamiltonian has a lot of indices. So the j there indicates that this Hamiltonian is used to encode the jth component of the data. And the k means that like possibly there can be other encoding gates which also encode the jth component, but which use different Hamiltonians. So to make that more clear, like there can be like a whole variety of encoding gates here which encode the first component of the vector x. And each of those can use different Hamiltonians. Do you have a question? No. Okay. And this can be the same thing for all D components. Remember, X is a vector in Rd. And now what I'm going to do is I'm going to call this entire set of Hamiltonians the data encoding strategy. Like this is the strategy that you've used to encode your data into the quantum circuit. Okay. So now we can ask what class of functions can we realize? And a while ago, Maria and I thought about this together with Johannes from Berlin. And what we realized is that we know that these functions are of this form, and it turns out that you can write them as this form. So basically, notice what this is that it's the sum over complex exponentials that have an inner product there with some vector which is coming from some set, and these are all weighted by some weights. And the point is that this set of, I'm just going to call them frequency vectors for now, which occurs in the sum, depends only on the data encoding strategy. It depends only on the Hamiltonians that you use to encode your data, not where you put them. That's completely irrelevant. It doesn't matter where in the circuit they are. Like, you know exactly what frequencies are going to appear in the set just by knowing the data encoding strategy. And then, like I told you, the order of the encoding gates doesn't matter. And then these coefficients can presumably be in some range, but like which range they're in and like which values they can take, how they correlated with each other, this depends on the whole circuit in a way that's totally unclear. And if someone can give me like a concise insight into the dependence of these on the circuit, I'll be extremely grateful. But I think this is hard. Exactly. So the point that really important point I want to get across is that these models all realize functions of this form for which we know exactly, if we know the encoding strategy, we know exactly what that set is. Okay. Okay, so just to give you some like small intuition that, sorry.
I'll wait for the end of the slide when you explain it.
Just to give you some small intuition, like remember that the data is in RD, and it turns out that this the set from which this vector comes is also a product set. So there's like a set of possible values for the first component, a set of possible values for the second and to the dth. And okay, this is somehow technical, but basically if imagine this is the Hamiltonian, the first Hamiltonian that you use to encode the jth component. This is the second Hamiltonian that you use to encode the jth component, and this is the third. And imagine H1 has 3 eigenvalues, H2 has 2 eigenvalues, H3 has 3 eigenvalues. Basically, you construct this tree where the leaves hold the sum of all the eigenvalues that you had to get to that leaf. And the set of all the frequencies is just the set of differences between all the leaves. Like, I want to go through this quickly. It's not so important, but like this is kind of how it works in practice. OK, now I'm going to tell you something very important. I'm going to show you that re-uploading PQC models are actually linear models. And this is going to be the key thing that we use when we try to dequantize them. So the question is, what structure should Bob exploit? Like, he's given the data encoding strategy. Alice has told him this. And like now Bob has to think about how he should design his learning algorithm to be better than Alice's. And what we do is we note that these PQC models are linear with respect to a feature map. So how do we see this? OK, we know it's of this form. The first thing that we do is we can decompose this complex exponential into causes and sines. And then you get some splitting of the C into A's and B's. And then what you can do is that you note that you can write this as the inner product of some parameterized vector with some vector which has taken X into a bigger space, into a feature space. And basically, what you see is that this feature map from X is just like you have the cos of omega 1, and then you have the sine omega 1, and then the cos of omega d, and the sine of omega d. And then, of course, C theta should just be the A's and the B's. So when you take this inner product, you get A omega 1 times cos omega 1, B omega 1 plus sine omega 1. It's clear that this realizes that. OK, but now we have like an entire arsenal of classical methods that we can try throw at this. Linear models are extremely well studied. OK, and remember that this feature map depends on the data encoding strategy. So these frequencies that appear here depend on the data encoding strategy. And the coefficients that you get here depend on the trainable parameters on the circuit. OK, but a very important point is that almost always these PQC models, so we know that any function realized by a PQC is going to be linear in the sense that I just showed you. But it's important that almost always they can't realize all linear models. So basically, you could consider the set of all linear models with respect to that specific feature map. So that's all models which are of the form of the inner product of some vector W with the feature state. And the set of all linear models you get when you consider all the vectors W. And then you have the PQC models, and they're a subset because these coefficients are constrained by the circuit architecture. And you can come up with a universality proof that shows that if you design your circuit well enough, then really you can realize all these. But like for practically realistic architectures, they cannot. OK, like I said, this is not well understood. But now, what is variational QML doing? Implicitly, what it's doing is it's searching for the best linear model within this subset of linear models. So you start at some point, you have some random initialization, you do a gradient step, you go somewhere else, another one, you go somewhere else, and then finally you end up there. The point is, you're in this set, which is a subset of all possible linear models, with respect to this feature map defined by the data encoding strategy. OK, and now we can try to start dequantizing regression with parameterized quantum circuits. And what we're going to try to exploit is this fact that they're linear with respect to a feature map, which we can extract from like the circuit description Alice gives me. And so if I want to try, so PQC models are doing it seems that they're doing some sort of subset of linear regression. They're doing a sort of gradient-based linear regression. But the first thing you should think of is, well, why can't I just do linear regression? After all, I know the feature map. So we should be immediately reminded of linear regression and kernel methods. This should be the thing that we want to try first. So here's I think, let's go through a primer on what these are. So in linear regression, you're given some data, let's say here in R2, and what you look for is the optimal hyperplane. This is what people talk about, the optimal separating line. And this is what people talk about by linear regression. But it could be that there's no linear separator for your data. So the standard tactic is to create a feature map, a map which takes the data from RD1, here D1 is 2, into RD2. So here, like, I've drawn a very bad drawing where I imagine that this feature map phi takes my data from this 2-dimensional plane into 3-dimensional space in such a way that when I do linear regression now in R3, like, these can be linearly separated. Okay, linear separate exists. So this is kind of the intuition and idea behind linear regression and associated kernel methods. But the key important point is that we know methods to find the optimal hyperplane in feature space. Like, these are kind of the first learning algorithms that people ever came up with. And so can we use these to dequantize this PQC regression? In particular, basically, we know what feature map PQC regression is doing. So can't we just run linear regression like using this feature map? This is what we should be thinking. Yeah.
I mean, you could push back in saying that the subspace search actually helps in some ways.
For sure. And like, this is like, tackling that is going to be the key difficulty that I try to overcome. Yeah.
Well, do you have any assumption about the difference between the information geometry of classical feature map and quantum feature map?
So here, like, I'm here in this talk, I'm only considering one very specific feature map, which is the feature map defined from the data encoding strategy of Alice's circuit. Like, in principle, you can consider like any feature map you want to try learn. But here, all Bob is trying to do is beat Alice. And so he's going to try to do linear regression using Alice's feature map. Yeah. OK, so now I have to give you a primer in linear regression. So if you just are in RD1, like there's no feature map, then you can find the optimal hyperplane with space complexity OND1 and time complexity that. This is how the algorithm works. But now maybe you know there's no linear separator, so you want to go into feature space. So you introduce some map which takes you from your original space into a higher dimensional space. And basically then you can also run linear regression, and now you get the exact same complexity, but the dimension of the feature space comes in there. And then what people noticed is that, well, actually what you're doing here is like you're calculating the inner products of all the data that you have. And so if you have a clever way to calculate inner products between data, like this, which is people call a kernel matrix, if you can do that more like faster than you could do linear regression, then you get an algorithm that has space complexity order n squared and time complexity order n cubed. And like this has an advantage when the dimension of the feature space is much larger than the amount of data you have. So this is like the one, yeah.
So okay, what sort of dimension are you getting in your feature mappings?
I'm gonna get to this.
Okay. Okay. Cool.
Is it D1 cubed rather than D2 cubed in the first?
Yeah. A mistake. Thanks. Great. Yeah. Okay. So now, like, I think we have all the tools to try a first naive dequantization idea, which is simply run classical linear regression using the PQC feature map that we can construct efficiently given Alice's circuit. And remember, Bob knows this. That's great. So we have the set of all linear models with respect to this feature state, the set of all PQC models. Alice does PQC optimization. And what Bob does is linear regression with respect to this feature map. And remember that the dimension of the feature space is equal to the number of frequencies. It's actually a factor of 2 there, but I'm going to make it easy. Just say that it's like equal to the number of frequencies. Unfortunately, there's 2 problems with this. The first one is exactly what someone just mentioned, that this has exponential complexity for Bob. Why? Well, because the space and time complexity depend on the dimension of the feature space, but the feature space dimension is equal to the number of frequencies, and the number of frequencies comes from a product set, and if each of them have n frequencies and there's d of them, then you get order n to the power of d of them. It's an exponential space that comes from the product structure. Okay, that's bad. The second thing is what Zoe mentioned, that the generalization performance of linear regression can be really bad. Because essentially we have that Alice finds some solution in here, and Bob finds some solution here, and Bob's solution is guaranteed to do better on the training data. He finds the empirical risk minimizer. This is a beautiful thing about linear regression. But maybe Alice does better. Maybe Alice does better on unseen testing data because she's had some inductive bias, like she's searched a subset. So basically, we have this naive idea to do dequantization, and it has these two problems. And now we're going to try to fix both of them. That's the idea. And what we're going to use is a technique called random Fourier features. And how does that work? So basically, OK, and I have to say that this was not, I didn't think about this idea. Like in this really, really nice paper that I like a lot, some people in Paris, they both saw this naive dequantization idea and had this idea for how to fix it. And essentially, my contribution is to make the analysis much more general in many different ways. OK, so you have this feature map. It's exponentially long. But so there's d frequencies, and d is like an exponential in small d, which is the dimension of the space. And cool, thanks. I might go into the question time with the talk. Yeah. OK, but now, one thing you could do is you could say, let me just put a probability distribution over those frequencies. And instead of calculating the actual feature map and doing linear regression with respect to that, what I do is I just sample m frequencies from this feature map. And then I construct the approximate feature map, which only consists of the terms that I sampled randomly. And the idea is that, well, you want this to be an estimator to that, and then you hope that like the tail bounds work out in the way that you want them to, so that the overheads in complexity are not too bad. OK, so here is the RFF dequantization idea. This is my approach to fixing, not mine, the approach of the people from Paris to fixing the naive linear regression. So given the data encoding strategy, you choose a distribution over the frequencies. Then you sample m frequencies from this distribution. You construct the approximate feature map, which is now a map from Rd to R2m, because you only sampled m frequencies. Then you run a feature space linear regression with respect to this approximate feature map, and you output the function. This is Bob's algorithm. OK, now what is the complexity of this algorithm? Firstly, the complexity depends on how complex it is to sample from the distribution you've chosen. OK, so this is a tree. Luckily, this is a tree, though. And we know how to sample from trees pretty easily. You flip coins at each node, et cetera, et cetera. So there's at least some class of distributions that you can sample from efficiently. And then, I don't know how that appeared there. And then you run the feature space linear regression that has space and time complexity that's n capital M. And so we see that we've solved one problem of exponential complexity, because we've gone from complexity of order n times omega, which is exponential in d, to order n times capital M. And we get to choose m. So really, the question is, how large should m and n be such that the difference in the risks between what Bob outputs and what Alice outputs is small? And in fact, I'm going to do something even stronger. I'm not going to consider what Alice outputs. I'm going to consider the best possible function that Alice could output with her PQC. That's what the star is here. So like, I even give Alice the opportunity to search every single model in her space. OK, and so now we're going to answer this question of how large. So now this has the potential to solve the exponential complexity problem. But I keep in mind that what I need to be better is that I generalize just as well. So now the question we're going to ask is, this has the potential to make you less complex to run. But what I'm interested in, how complex should it be if I want to guarantee that Bob is as good as Alice in a meaningful way with respect to generalization on the unseen data? OK, and now some of you who know something about random Fourier features might think, I thought random Fourier features had to do with kernels. And so far, I haven't really discussed any kernel at all. Exactly. So I think I'm going to skip this slide, and I can come back to it if I run out of time. But the point of the slide is to connect what I've already shown to random Fourier features theory for people who are interested in it. OK, and now I can present you a theorem, which is the theorem that together, with my collaborators, we proved recently. And then I'll also tell you how it goes beyond what Landman and the crew from Paris did. So what we can prove is that linear regression with random Fourier features is guaranteed to output a model which is no more than epsilon worse than PQC optimization with respect to generalization, provided that n, the number of data points you need, is greater than some jargon, which I'm going to explain, and m, the number of samples you need to take, is greater than square root n log square root of n with some prefactor, which is also a jargon. And what I'm going to show you in the next slide is that this prefactor of m here depends on the probability distribution we've chosen over the frequencies. And this prefactor of, or this like thing which determines the sample complexity, the amount of data you need, depends on the alignment of the optimal PQC function with the probability distribution you've chosen. So basically what I've done now is I've like kept reducing the problem to a new problem. First I had to solve the complexity, so then I introduced random Fourier features, and then I try to analyze random Fourier features, and it comes down to analyzing whatever that is and whatever that is. So in the next 2 slides, I'm going to like give you concrete bounds on these things which allow us to say how expensive or cheap this is. Okay, and remember that the space complexity of this algorithm is n capital M. Basically, this depends on n and m in a polynomial way. And so in order for Bob to be efficient with respect to d, which sets the scale of my problem, so I mean, someone could also argue with me here like that this is a very computational learning theory perspective, that I'm imagining like an asymptotic family of problems with respect to the dimension of the input space. Like this is the natural way to do it, like if you come from a computational learning theory background, but I accept that like natural data sets maybe don't scale in this way. Like I think again, here I like concede to Maria that this like doesn't model practical situations so well, but it's the right way to do it if you want to set up an asymptotic thing. So in order for this to be efficient, we need to A, be able to efficiently sample from the distribution over frequencies, and B, we need that this prefactor here and that factor there are polynomial in D, and you can add a 1 over epsilon and a 1 over delta if you want, but I keep it out to be simple. Okay, so now the question is, when is this the case? Like when do we get polynomial scalings for these things which allow this to be efficient? And so let's look at the first thing, this 1 over t omega. And it turns out that this thing, which is like the norm of the kernel integral operator for those who are interested, is equal to the maximum probability distribution. And remember, there's exponential frequencies. That's going to be important. And so for this thing to be polynomial, I basically need that p max is like bounded below by an inverse polynomial. But what this means is that the distribution needs to be concentrated because there's an exponential number of elements in the set. And if I need like the maximum probability distribution to be like greater than an inverse polynomial, it means the distribution has to be concentrated. An example is the uniform distribution. So for the uniform distribution, like all the probabilities are equal to 1 over capital N to the power of D.
So can you repeat, what is this distribution? Which distribution is this?
This is the distribution that I choose. So in order to run random Fourier features, I have to like place a distribution on the like components of the feature map.
Yeah. So I mean, there's a reason why you cannot pick a Dirac delta in one thing. That's not good.
I'm going to show you like there's going to be some trade-offs that come in, and like this is one of the trade-offs. Yeah.
I know you're watching the time, but it's
Okay.
in random Fourier features, that distribution is actually nothing you choose. That
Yeah,
is given with the kernel.
That was on the slide that I skipped. Like I can give you the answer. The point is that it turns out that like you're right. In random Fourier features, this is why I skipped that slide. Like the distribution, you can't choose it. It's the inverse Fourier transform of the stationary kernel. But what I can show you is that like for any distribution I want, I can choose a kernel that has that distribution as the inverse Fourier transform by reweighting the PQC feature map in a way that doesn't change the class of functions that can be expressed. And so by that way, like this becomes a parameter of the model. And this is somehow like a really new thing that we saw. Like,
So you do something with your C's, and then you kind of take.
Let me go back quickly.
You factorize them and put that into your feature map.
So basically here what I do is like if I have a kernel, then I get the inverse Fourier transform, and that's how you normally do it. But now if you give me a probability distribution, then I can define a reweighted feature map where I just put like the probabilities here, and then I can define a kernel from that, and then that has this as the inverse Fourier transform, but it still has this property that I need for everything to work. Yeah. Yeah. Okay, so the first thing that we need is the distribution that we choose. The first thing that we need is the distribution that we choose is concentrated. Okay. Now, the second thing that we need is that this thing here, which is really the RKHS norm of the optimal PQC function, is small as well. And what this thing measures is the alignment between the probability distribution we've chosen and the frequency representation, that's what the hat here, of Alice's optimal function. Remember, we know that Alice's function can be written as like a combination of these terms. And so we can write out all the weights of the optimal function. And basically, it turns out that this thing here is small when these two distributions are aligned with each other. And that makes sense. Like imagine I choose a distribution which is not supported at all on the frequencies present in the optimal solution. I'm never going to find it. Like it makes sense that this can only work when these two things are aligned. Okay. Now I think I can summarize. So we saw that there's this naive way that you could dequantize PQC regression by doing linear regression. This is not efficient, and it maybe doesn't generalize. So what we do is we say RFF can address the complexity, but then we have to prove a generalization bound. And then we prove a generalization bound, and it depends on these two things, the RKHS norm of the optimal function and the norm of the kernel integral operator. And now, so that's like the distribution we choose, and here's the optimal function. And the point is that this RFF-based linear regression is an efficient dequantization method when P, the distribution that I choose, is both concentrated and efficiently sampleable, and P is well aligned with the distribution of the optimal function. This makes sense. Like none of this should surprise you. These are very reasonable. It's a pain in the ass to do it, but then what you get out is very reasonable, which is nice. And now you could ask me, okay, I've proven that these things are sufficient in the sense that I have upper bounds. Like if those are satisfied, then for sure Bob is efficient. But do those need to be satisfied in order for RFF to be dequantized? And well, so like I said, we've seen sufficient conditions. And are they necessary? It turns out, yes, they are in an average case sense. Unfortunately, I can't actually prove they're necessary for the exact same criteria. Basically, what I can look at is this kind of expected error over different runs of random Fourier features. So each time I do random Fourier features, I'm sampling a different frequency vector. And every time I do it, I'm going to get a different output function. And what I care about is the average error. And basically, what I can show is under some technical condition, if I want this average error to be small, then the number of frequency samples I need, scales like this. Again, it shows Pmax has to be concentrated. And again, under some technical condition, this number of samples scales inversely with the inner product of the Fourier representation of the optimal function and the probability distribution. There's a mismatch there, but it's a good start. And if someone wants to kind of close that gap, it would be nice.
So we have this result with the doubly exponential separation between all linear models and the heteroplodian ones, right? Yeah. Why is this not example already enough?
I mean, for sure, you guys and Sofiane is who is on this work with me. I should say that you can definitely not hope ever to dequantize all of PQC learning. This is very important. You can embed cryptographically hard problems into into this PQC framework. So
that's not what I meant. I mean, just proving that there exists data sets that need double exponential samples to learn if you're doing it with a linear model, where you don't need that if it's not a linear model. Right?
Okay, that can do the trick. I see what you mean. Here is a lower bound. I see your point.
Even though I've seen O's, you would have to have thetas, then you can.
Okay, now I see your point. Okay, so I have 2 minutes left of your timing, and I'm going to summarize. So in order to dequantize, we need two things. We need that P is concentrated and well aligned with the optimal function. But if F is going to be well aligned with P and P is concentrated, that means that the frequency representation of the optimal function needs to be concentrated. Okay? This is kind of the main thing. And so essentially we have the following scenarios. The first scenario is that the frequency representation of your optimal function, which is set by the problem that you're trying to solve, is concentrated. Then dequantization is possible, but you have to know the probability distribution and be able to sample from it. Because to run this dequantization thing, you have to choose the distribution. So it could be that in practice you know something about the structure of the problem you're trying to solve, and if what you know is a limit on the frequency range, then you might be able to dequantize it. But if you know nothing, you probably can't choose P so that it's sufficiently concentrated, sampleable, and aligns with F. That's an important caveat. But if this thing is not concentrated, so if it's spread out, think the uniform distribution, then RFF dequantization is not possible. And the real conclusion of this work, I think, is that here in this limit is where quantum advantages might be possible. And the question is, are there any interesting functions here when the optimal representation of the function is not concentrated in this precise technical sense with respect to the Fourier distribution of the frequencies? And so I think that's the conclusion. And I say I'm very, 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 very lucky to work with many amazing people. And this is them. And here's the archive links of the things I spoke about. I'm sorry for eating into lunchtime already.